Hello everyone, I'm Dario. I'm a third year PhD student at University of Turin and the Astrophysical Observatory of Turin. And I will talk to you about the measurements done, meteor measurements, observation done by the Mini-EUSO telescope on board the ISS. So basically I will describe what Mini-EUSO is as a first thing, and how we implemented some algorithms to find actually meteors on Mini-EUSO data, which is not as an instrument thought for detect meteors. And then we will go over some results from that analysis of these meteors that we found in our data and simulation to interpret those data. So Mini-EUSO is an experiment in the framework of the Mini-EUSO program, which stands from Joint Experiment Mission for Extreme Universe Space Observatory, which main goal is not about meteor, but is the detection from space of the extensive air showers that are generated by ultra-high energy cosmic rays. This is interesting in astrophysics because ultra-high energy cosmic rays are not deviated by stellar magnetic fields, so they point straight to the sources to their sources. And so these are, in the astrophysics particles, very intensive events. And so for this kind of purpose, we look from space at the Earth atmosphere, which is just like our detector. And of course, looking the Earth atmosphere, we can see many things. For example, meteors and other things like lightnings, transient luminary events, space debris, the Earth emission of the Earth itself. And Mini-EUSO is a pathfinder mission. So Mini-EUSO is a multi-wavelength imaging new instrument for EUSO, so Extreme Universe Space Observatory. And it is the first instrument of the GEM-EUSO program which has been installed in the ISS. It is installed on an UV transparent window since air showers emits in the UV wavelength band. And it was installed in 2019 on the Russian Zvezda module of the ISS. And it is operative to date. Since the first session, the instrument is not on all the time, but it operates in observative sessions. We have done up to now about 60 sessions. We have some session per month. It is, let's say, a scale version of the original GEM-EUSO telescope, which was thought to be having 2 meters lenses, while this is 25 centimeter Fresnel lenses. And it looks, as I was saying, in the UV range. So the peculiar thing about this instrument is that since it is thought for detecting air showers, so cosmic rays events, it operates as a very short time scale, which is this first one, 2.5 microseconds. Of course, for meteor is not good. And but the interesting thing is that the GEM-EUSO collaboration, Mini-EUSO collaboration, managed to have a peculiar data acquisition, which takes data in 3 different time scales at the same time with the same instrument. So we have 2.5 microseconds, which is cosmic ray time, let's say, this time multiplied by 128 times, so 320 microseconds, and then by another multiplication of 128, we have 41 milliseconds approximately, which is good for meteors. And so while the first 2 time scales are triggered, because otherwise we would have too much data, of course, that it also has to be downlinked to the Earth. The D3, so the longer time scale, is not triggered, so we had to look for meteors in this kind of data. And we have, of course, a very wide pixel because the pixel on ground has a footprint of about 6 kilometers, so it's not highly precision measurements. This is an example of a very bright event. I think the brightest event that we detected with Mini-EUSO. And so the trigger is operating on a pixel level. this image is a reconstruction of the event, but actually the actual data suffer from differential efficiency differences between all the pixels. So there is a heavy manipulation of the data to come to this nice picture. And for now, since we have not that much of data, we have this trigger that operates automatically on D3 data, and then we select by visual inspection, because since this is a very general purpose instrument, we have a lot of events like lightnings and ground sources. And these are the results of the meteors that we found on the first 14. Actually, the first 4 were test sessions, so the first 10 sessions of Mini-EUSO. And the important thing is that we observe meteors with a rate of about some meteors per minute, sorry. And also the intensity of these meteors I will show after. The limiting magnitude, which is about +5, +6, is consistent with what we expected, and at this magnitude, the expected rate of meteor is consistent with what we observed. And this is an example of increasingly dimmer events seen by Mini-EUSO. Of course, you always see something on the background, which is I don't know, clouds or Earth signals like continents or countries. Okay, and so to analyze this peculiar data, we also developed a dedicated reconstruction armory. Of course, we do not have stereoscope vision, so we cannot triangulate. We have to make some assumption, but we can deduce some parameters about these meteors. And basically, when we have the information about the trigger, there is an automatic reconstruction. So on the field of view, all the pixels that are interested by the event are detected and selected. And in this way, we can reconstruct the whole meteorite curve and the position of the meteor as a function of the time. So this is the results, the X and Y position and the intensity, the net intensity of the meteor itself. And from this data, we can derive something like the duration, the direction, so the azimuth, the horizontal speed. We don't have the vertical triangulation, and the magnitude, also assuming some altitude for those meteors. Okay. And these are the distribution on the first data set that we have, so the first 10 sessions. And these results are consistent with what we expected for the azimuth distribution and also the speed distribution. So we were happy about it. And we, as I was saying, and this is written in the title, we look in the near UV, so roughly from 250 to 450 nanometers. And of course, this is not a common wavelength. And we don't, for now, we don't have laboratory measurement of the efficiency. We have something. So for now, it is a rough estimation of the 0-point magnitude, the magnitude of the meteor itself. And so this is just some data about the Mini-EUSO wavelength, bandpass, etc. And so basically, the bandpass is the thick line here, the black thick line. And this is the result of the magnitude distribution. Of course, one thing that we can do with this data is to compute the population coefficient, population index. But if we dig inside the data, we can find out that there is, of course, an observational bias. So we observe faint magnitude, so high magnitude meteors only with optimal background conditions. So with background counts per frame, which are 0, 1, from 0 to 1 counts per frame. So this has to be corrected to derive an actual population of meteors that we observe. So the observational bias must be corrected. And this is what we are doing now. So we implement the dedicated simulations to be able to determine the exposure of the instrument as a function of the magnitude of the meteor and a function of the observational condition of the meteor, of the observed meteors. And this is mainly part of, so the exposure is time and area and angle. So the area part and the angle part are constants for our observations. But the efficiency, so the time is the question in this case. So we implemented this model and basically to generate a population of meteor, we randomly sort on these quantities. I will not go through, basically the equations. And so we randomly sort of over all these quantities to generate a population of meteors with all, I don't know, asteroidal commentary and whatever. And this is an example of simulated events in here. And we have the same data that we have on real data, so the same results that we have on real data. But now we know the actual magnitude of the meteor, the actual speed, so we can have some results. And basically, this is the last slide, and this plots the trigger efficiency. So the efficiency in which a meteor is detected by Mini-EUSO and successfully recognized by the trigger algorithm. And there are two, because there are two layers of trigger. The final one is the bottom one. And what is evident, of course, is that there is a decreasing of efficiency as a function of the magnitude and also as a function of background. And this is the basis for the computation of the exposure. And this is what we will do in the, let's say, near future. And we are now working with some students to apply these results to the actual data being used. And so basically, that's also the conclusion. The main conclusion is that Mini-EUSO, which is not an experiment for meteors, is trying to contribute for meteor science. So this is also something that we published in a recent white paper, telling that meteor science can be done also with other instruments, not just primarily meteor instruments. So there are in the world a bunch of instruments that may detect a large data set of meteors, but these data are not used yet. And so this is a work done for these instruments, and yeah, we are doing, and we will publish results, I think, end of this year or the first period of 2023. So thank you for your attention.
Thank you, Dario. I see a number of questions from the audience. Peter?
Yeah, thank you very much. Very interesting. And could you give us an idea why you use a Fresnel lens as an optical system?
Yeah, because the using of Fresnel lens is thought for the original purpose of the instruments, which is detecting cosmic ray showers, and the Fresnel lenses allow to have overall dimension of the instruments itself, which is smaller. So the fact is that we have to bear in mind that these instruments have to be shipped to space, and so the smaller the instrument is, the better is. So yeah, the Fresnel lenses allow for a wider field of view with a smaller lens, so a small dimension of the instruments, smaller dimension of the instruments itself.
Is it one lens or a combination?
It's two lenses. Yeah.
Okay.
It's two lenses.
Sorry, but what were the main advantages of using Mini-EUSO rather than any other sort of satellite, for instance, like can also take a picture from Earth, or is that easier than that case?
Many satellites doesn't have that time scale, so that frequency, okay, for 40, 20, 30 Hz, okay, so many satellites doesn't have. And I mean, there is no advantage. I mean, in fact, I say there are a lot of other instruments that can be used for meteors, and that are not used yet. So this is what I'm trying to say. Okay, so there is no clear advantage. Mini-EUSO has a low resolution on ground, so it's not optimal in some senses. But this is the message. So there is no. The fact is, many other instruments could be used for meteors observation in space, of course, and some of them are with limited, let's say, limited results for now. But yeah.
Great, thanks. Great presentation.
Thanks.
Another type of camera is the doorbell camera.
Sorry.
The doorbell camera you can also use for meteor. So let me check, is there any?
No online questions.
No questions on the chats?
Okay.
Okay, although
Thank you.
no other online participants? Okay, thank you, Dario.
Thank you.
So the next three talks, they are on the Tower Hercules. And the first one is by Norton Sabel. Welcome.
Okay. Yeah, last Lokish also talked about this expedition briefly yesterday. Probably most of you remember, even though we had a rough night. So there was an expedition to Texas. Unfortunately, I wasn't there, but since they came back, I'm taking part in the inspection and unlighting of the meteorites. The meteors. Please click back. Yeah. So our venue was the McDonald Observatory in Texas. They had a long flight, and why this is so good? As you can see over there, it's in the middle of the dark sky area. So the visible limiting magnitude was around 7 magnitudes, and we think that with our instruments we picked up stars and the meteors, which was around 8 magnitude in brightness. So dark skies were a priority. We use an All-Sky 7 camera and also a DMK and a Sony Alpha 7S and also a Karl, which is shorter for battery. So as Laszlo said, if the skies weren't that clear in Texas or near the McDonald Observatory, then they could go somewhere to the desert, maybe to have a clearer sky. Fortunately, they had amazing nights, and it was a success. Our method was first, of course, record the meteors, then find them, try to get the coordinates, and them, and use those coordinates to get radiance, and then with some other methods get some more science out of it. So the recording was made also in audio, and we have a video files, of course. The audio helped us to count how many of the visible meteorites were actually visible. So how many of them were observed by our team. There were 6 of them, and
pytanie, co mają robić ci, którzy borykają się z drożyzną.
Yeah, so there were 6 observers, and counting the bars when they counted, we estimate that they saw around 220 meteors by the naked eye in the first of May. Please click back into the presentation so it's active. Thank you. So then we had to search through the files. We had around 3.5 hours per night, and we had several problems. With the Sony Alpha 7, we got an ISO of 40,000, which generates a lot of noise. So we couldn't find an easy solution with softwares. Also, there was the problem that most of the meteors were very short and very faint, and they also appeared mostly in 1 or 2 frames. So it was really hard to detect. So normal traditional methods are out from the field. So we had to use some neural networks, biological ones, actually. So we got the idea from Peter to have a flat screen, and we started observing them. Yeah, it took a lot of days. So even we were 4. We had like 5 or 6 sessions when we were working through each of the meteors. So that was what we saw, a huge TV, and we divided it into quarters. So we didn't have the problem what Peter mentions to. So when we look in one side of the screen, then we miss all the meteors on the other. So each of us had one quarter of the screen, and we actually tried it with multiple people. So first, there were only 3 of them, and they saw some meteors. Then we tried it with 4 people, and we had a jump. So we noticed 50% more from 3 to 4 people. So this is our advice if you are watching it alone, like Diavol or Peter, if you did it alone, or the others who process video like this, do it with more people. You will have significant improvements in meteor sighting. But when we jumped from 4 to 5, there was no significant improvement. So like 1 or 2%. So we paid usually at 4 people, and it was a feeling that we had to have a warm-up time to adjust to the atmosphere of meteor sighting, and usually it was like 50-minute, a 30-minute video was 1.5 hours of processing. So it's a long program, and you probably see why. There is a meteor in this small video over there, if any of you noticed. If not, then this is not ideal. Firstly, because we have a drawing on the presentation, but other than that, so these are not ideal lightings and all, but I cut off a small part of our video, so let's try to analyze it. I will play it about 10 seconds, and you have to count how many meteors you see in that 10 seconds. I will only play it once, so yeah, and the online participants can take it into full screen, and they have an advantage over us. Yeah, fine. Okay. How many of you saw only one? Raise your hand. 2? 3? 4? Okay, there were 8 of them. So there were 8 meteors. So now you get the problem. So ideally, we might have to watch it again and again, and we actually did it. So we repeated some videos, and our feeling was right that we catched around 90 to 95% of them the first time. So it's an optimal number of people for to watch this kind of video. Then the processing. This is the part when I have to mention that we are newcomers to the meteor business, so we have no idea how this works. So we have to make it up in a way. So it's a really handmade and craft method of analyzing. I cut off the frames from the meteors and used max stacking to have actual files where the meteors are visible. Then we use astrometry to get the fixed files and the coordinates of each meteors. And then was the fun part when we manually had to find each meteors and get the coordinate. And once again, I invite you for a fun game. Which one is the meteor? If you guess this one, well, you are wrong. If you guess this one, you are wrong. And this isn't it, and this isn't it either. It's there. Thankfully, we had a feeling that we will have problems with that. So when we were searching through the videos, we always recorded the polar coordinates approximately where we saw the meteor. So that was like 7 o'clock and 50% down. So if we had an easier time, we made it easier for us to find that. But it was still hard because we had like 800 meteors. Searching through them by hand wasn't an easy task. This is the raw data from the 31st of May. We cannot really see any peaks. This is visible, which was also there in the other data. So maybe there was something around 4:30, but this is a really flat distribution. So there is no conclusive maximum activity right there. And if we compare it with the noise, the sound, then there isn't really much there. So there is no correlation between what the video saw and what our observers saw, which could also mean that the size distribution was totally random. So there were many faint ones, there were many bright ones. It was flat all the way through. Then we started to searching for radiance, and first we had a feeling just by looking at the videos that there are multiple of them. The first method was just to have a line, a great circle fitted into each of our meteors and find the crossings of all of them. This is not so much helpful. So then we refined it a bit, and we had a graph like this. When we grabbed meteors that we were pretty sure were Tau Hercules, and then we only watched their crossing with sporadic meteors. So it's almost like a random part of their trail. And now we can see they are converging somewhere there. We can also feel that there is a radiant, but the conclusive part was this when we only counted those that are not sporadic. We thought they were not, but as you can see, we had many just random meteors all the way there. So we got all that we thought was Tau Hercules. Then with the 1 sigma bar, reduced it to these greens, and then another 1 sigma, we had this blue. So that is right now the most precise radiant approximation that we have for the Tau Hercules. So what's next? We are still working, so we have a lot to do. We have a feeling that maybe there is a special distribution, maybe by size and the length of the meteors, or maybe by brightness. We didn't have time for now to check it. We are still not convinced that there isn't any other radiance, so there might be, and if so, maybe their activities were shifted a bit in time. We of course have to make something which is easier to use, because sitting down in front of a screen for 11 hours is not the definition of fun I would use. So we have to create a more fluid pipeline, and we haven't really touched the DMP and the All Sky 7. So there is raw data also there to use and to analyze. And the most important part is that next time they take me also, because otherwise I don't know, I will smuggle myself onto the plane. Thank you very much.